So this is another topic in again, it's related to dimension reductions, and the name is singular value decompositions. We call it SVD. And this is like the topic that you're supposed to learn from when you take the linear algebra. And so we have to spend a lot of time to for me is to teach like what the singular value decomposition is, but I'm gonna skip a lot of things. I'm gonna skip a lot of details. But what I want to do is that to give you insight, and later on, I will show you how to compute the SVM in Python, right? And I'm going to more focus on how to use the SVMs for the dimension reductions or like approximation, things like that. Okay. So there's some you have. I mean, suppose this is linear algebra class, and again for linear algebra, this matrix is really important. And suppose we have any kind of matrix A. And at the beginning of this semester or these lectures, I think I say A, we can think of related linear transformations, and vice versa. Whenever you have linear transformations, you guys hope that you guys are able to come up with matrix A. Okay. So this is the starting point. Suppose you have any kind of matrix, then it's linear it's same as linear transformations, right? And having proper coordinates, any kind of linear transformation that then you guys can think of as a combination of rotations and stretch or compress. Rotations and stretch or compressions. If that's linear transformations. But the good thing is matrix it's linear transformation. Okay. Then let's see this kind of plots or figures. And suppose you have some data points here. Then this is AX. And probably this guy is gonna transform into here. Like this data points right there. And this data points is like there. So whenever in the original space, we're gonna say domain by matrix A, we'll do transformations into other space. We call it range of A. And by looking at here, say if you have a circle like that, unit circles, we're gonna unit circles rotate it, and in that case, stretched and compressed by A. There are a lot of things that I can say and we can discuss, but I'm gonna skip all of them. But imagine or visualize it in unit circles by any given matrix of A, rotated, stretched, or compressed. Okay. And what we can do is vector v over there, this AV2, this guy's translated AV1. So this one is sigma 1 U1, and this one is sigma 2 U2. V over there in domain of A is V1 and V2. In range of A, it was U1 and U2. You do the eigenvalue analysis, it was like, I would say V1 is lambda 1 V1 and A is V2 lambda 1 V2. In that case, its domain and range are the same, and these two vectors are the same in domain and range. But in more general case, U and V's are different. They are in different space. So I guess this SVD is, I mean, the eigenvalues and eigenvector or eigenanalysis, very special case of SVD. Okay. So SVD is more generic expressions. We can apply like any matrix of A. So, okay, so I guess with these, the concept of SVDs, we can do a lot of things. We can do a lot of things. Like, so that's what we're gonna do over there. So actually it's related to row rank approximations, which is related to dimension reductions as well.